Good afternoon. We have come to the 8th week of this course, Advanced Computer Architecture CS 470. We have closed with last week the first chapter of this course on general purpose architectures. We have seen two main branches, how to go about building machines statically scheduled and dynamically scheduled, and in different contexts, both ideas work very well. Now we move to application-specific computing, that is to computers that are not used as general purpose computers, but are used for very specific application inside other products that are sold not as computer, but as something else. We will proceed in a slightly in natural way, if I may say, because it would be natural to start from the digital signal processors that are one kind of processors that in some sense are relatively similar to general purpose processors, but start to have some specialization to the to a class of applications, and then move into instruction set extensions and high-level synthesis that goes to the direction of saying, okay, I'll take my program and I'll create directly circuits. Doesn't matter that they are processors, they may not be processors at all, in fact. Instead of that order that again maybe is a little bit more natural, I'll proceed. I typically swapped. It happened also last year. I swapped the two parts, if you want, and I start from instruction set extensions and high-level synthesis, just because this will help with the scheduling of the third homework, that is an high-level synthesis exercise. So slight change, slight reordering. We'll come back to more processors more similar to what we perhaps would expect in exactly 2 weeks. Note, by the way, that this video will be pretty long and covers also part of the next week, where there will be also some other video to complete the two lectures. To open this part on embedded processors, embedded processing, I think that there is an experiment that was done at the beginning of the millennium that I always find interesting, and it is not dating too bad. I mean, it's still an interesting point. It's represented by what you see in this slide, where you have the size of 4 generations of a processor, of the alpha processor. I may have spoken about alpha a few other times. It was a very, very nice design. It was a fairly late RISC design compared to many of the others that we know, including Power PCs and so on. And it was one of those that was more clean and using everything that people had learned from the first RISC design. So it was actually a superb processor, and in many cases it introduced new architectural ideas before anybody else, and actually managed for I think a couple of times to sort of Digital Equipment Corporation, DEC, the company that was doing this processor, managed to get ahead of Intel in performance in a couple of times. And this has been extremely rare in recent history, recent being the last 3-4 decades. So it's a very, very clean and interesting processor. And what this exercise, this slide shows is what if I take 4 generations of alpha, starting from a in-order issue 2 processor, a superscalar in-order issue 2, a version issue 4 still in order. I think it was the first actually out-of-order commercial microprocessor, issue 6, but again, out of order, dynamically scheduled, and a version that was out of order issue 8. Actually, EV8 has never been manufactured. Maybe I mentioned it already when we were talking of, let me remember what, of simultaneous multithreading, because EV8 would have been the first processor with simultaneous multithreading. It would have probably appeared before any simultaneous multithreading by Intel, except that Digital died, went bankrupt, and sold the activities of Alpha to Intel. And then probably I told you the anecdote that very soon Intel came out with the first simultaneous multithreading processor. So EV8 minus is a version of EV8 that never existed. Actually, EV8 itself never existed, but is a version that is reduced by pretending that the simultaneous multithreading is not there. So what is the purpose here? The idea is to look at the real estate, the silicon real estate, so how big these processors are. But what is very peculiar is that whenever these processors came out, they probably were around the 2 square centimeters that typically processors are. Why 2 square centimeters is it has to do with yield, right? You want to have processors that have used as much as possible the technology that you have to be as fast, as performant as possible, but they cannot be too large a die because otherwise yield goes down, right? The probability of having a defect becomes so important that you throw away too many. So this is actually a rule, and a rule that doesn't change too much with technology. In any technology, at any point in time, in the last 20, 30 years, processors, top-end processors are around, say, a couple of square centimeters, something like that. What you see here, though, is not how they looked when they were manufactured, except for EV8, that is probably in the technology for which it was conceived, and you see that is around these 2 square centimeters that I was mentioning. But all the others were produced in older technologies, so were actually bigger when manufactured. But now we see them, so the work that these people that performed this experiment did has been to remap these old processors from the informations they had into a newer technology. What if today I were to implement EV4 on the same technology that I'm actually using for EV8? And of course, it becomes a very small processor, right? Because it was a big processor at the time, but the many nodes passed, right? More slow every time, they're half the size, and therefore they become smaller. So what is interesting? What is interesting is that you never see them this way, right? Basically, processors have grown in size hugely. In the same, so the area here means essentially transistors, because the transistors are in the same technology and so are the same across the four generations. The number of transistors that went into doing processors has been growing hugely. Part of this is certainly caches, right? Very large caches, multiple levels of caches, but part of it is also that we've been adding things that were not, right? So as a sort of little reminder of the beginning of the course, right? These are in order, so the scheduling is relatively simple. It's just a question of checking dependencies, and here we have out of order, so we start putting reorder buffers. Here we have reorder buffers and reservation stations, but since issuing goes up, probably the size of these reorder buffers goes up quadratically, so it's much bigger, and so on and so forth. Right? Okay, so this is one thing that is maybe astonishing if you look at it well, right? The number of transistors, the area went up very dramatically in general purpose computing. And again, this is why is it interesting that is alpha? Why maybe these people chose alpha? Partly is because I think some of them had connections to the alpha team, so had some information that maybe was not publicly available, but also the fact that it's a clean processor, right? There are no history, no problem of compatibility that somehow distort the picture. This is the picture, right?
And then you do the experiment about performance, right? And you say, okay, so what will be the performance in the same technology of these processors? And what you get, maybe these numbers are not completely reliable, but they have been done with some accuracy still. And you see here the instructions per second, right, performance across the execution of I don't know what. If you see the paper, you'll see it, but probably some classic benchmarks. And you see what happens, right? There are many places where actually the difference between the different processors is very small. In some cases, is almost nihil. And in the best cases, you have situations like here. This is time, right? This is the committed instructions, which means wall clock time, basically. You do have EV8 that is committing many more instructions per second than EV4, but the difference is essentially represented by these numbers, right? You have something that is, you have done something that is 80 times bigger in area, and it gives you only, and I think the only has to be in quotes, right? But still only 2-3x performance. Now, 2-3x performance is good, right? It's not negligible. What we are looking here is that at the pure architectural improvement. So in a sense, we feel good, right, for this course and for what we have done, because this is exactly what we have been studying, right? How to bring up the IPC, and the IPC has gone up fairly significant between even some early superscalars to out of order superscalars, some, I don't know, 10, 15 years later, right? So there has been a very significant increase in performance. So this works. What we never measured, and this paper measures, is how much is the cost of this increase in performance. And the cost is way bigger, right? Way larger. And also, if you look at the performance is also wasteful. It corresponds to my sort of joke at the beginning of the semester, if you remember, right? When I asked you what is the first optimization criteria of a computer architect is performance, what is the second is performance, what is the third one is performance. Again, it is a joke, but it's what this exactly shows, right? I mean, what cares is not that we reduce power or reduce area. What cares is that we get performance, right, at somehow all prices. Now, the point of what we are going to do in these coming 2 lectures, today and next week, in fact, also, sorry, in the DSPs, so from here to the end of the semester, in reality, is not everyone can afford this price. Price in the sense, in a extended sense, is not only the dollars to get a chip that is so big, which is certainly something that you cannot afford too much, but also cannot afford the power or the power dissipation, and therefore the temperature that this would lead. So you want to get performance in some cases, because performance you need also in embedded situation. You need it in your cell phone. You need it in some embedded hardware here and there. But you cannot pay this high price, right? And so this means that basically what you do in systems on chip, in embedded situation, is very different from what happens in traditional general purpose computing. And DSPs that we'll see after this course, in principle, in my mind, you would have seen it before, will be an example of exploiting this. And we will continue in that direction. So this is a bit the menu for today and next week, right? Is looking at, I start from C programs, let's say high-level programs. Of course, my colleagues, more software-oriented, probably laugh when I call C a high-level language, right? But it's higher level than anything in the form of both assembly language, if I think software, or because we'll will go there if I consider Verilog and VHDL, right? C programs is functional description of what I want the program to achieve, right? And so we want to go from C programs to more efficient solutions, right? And we don't care too much programmable what it means. What we care is we want to have something that works faster for less, right? For less than this. So what can we do? And we'll go, the menu for these two lectures will be in three parts, right? The first is to say, okay, we'll take a processor, but we'll do something on the processor to make it go faster for that specific program, right? So we will not do a better architecture in general, in the sense that I can put there any program and almost any program will benefit from the modifications I've done. I'll do much more surgical, maybe, modification to the processor, but in such a way that that application, that program, or a few programs of the same sort, of similar sort, will get this performance benefit. So essentially, we'll try to do exactly what was maybe in this slide, get the performance and try not to pay the price. The loss will be in terms of generality. And then we'll go in the direction of losing completely the generality and the extreme case of essentially what we start doing already here, which is this HLS that I probably used already without defining, high-level synthesis. And the idea is exactly to go from C programs, or from programs, but usually in practice today it's almost always C, C++ programs, into hardware. And this is a funny way to do hardware because you'll see it very soon, but this is very clear. We want to go from this to hardware. There is no processor involved anymore. Forget about processors, but we want to do computing, but it's a different form of computing, right? It's a circuit that does the one thing that I specified in my program. And we'll see a couple of ways to do this, and we'll discuss the difference between the two. So let's start with the first one, which is this idea of processor customization, and actually automatic processor customization, and we'll come back to the importance of this word. So a few years, 10, 15 years ago, maybe even a few more, it had become relatively popular to look at processors in a more modular way. Instead of looking at a definition of an instruction set and having a processor that is my x86 that I go out and buy, my Core i7 or whatever it is. What I have is a more composite description of the processor. Tensilica was one of the companies that was more pushing this direction, and had a processor or processors, more than one, but they looked a bit like this. I think they had, if I remember correctly, they had a generator on the web where you would actually click a few buttons to specify what you wanted, and you will get something that is the composite of what you see in this image, right? You see the blue and the green part, and if you read in the little boxes, what you imagine is a simple RISC architecture, right? It has a fetch decode unit, it has a basic execution pipeline, it has, of course, register files, some ALU, a load store unit, whatever you need, right? The basic things that you need, control stuff. And this every processor needs. Some of the things can be changed, can be customized. For instance, the register file, right? You can do a processor with 16 registers. You can do one with 32. You can do one with 64. Provided that your instruction set supports this number of registers, which is an encoding issue and probably an easy one to solve. it can give you some advantages because the more you have registers, the least you spill. But if you don't have many variables alive at the same time in your typical program, it's a waste both of encoding, so of code size, and of registers in the hardware. So you can configure these things. And again, they were doing these things on the web. Maybe they had only 2-3 points, right? 16 or 32 or 64, something like this. Then you have a bunch of functions that are optional, right? You can have additional functional units to do some very special operations, for doing DSP operations, additional load store units instead of a single one, or local memories, and so on and so forth. You can read at the slide. And then it opened to a third part, which is actually something that is not designed at all, and is something that you write yourself. So essentially, you have some interfaces to circuitry where you do what you want. So you have here, for instance, a user-defined execution unit, something that takes maybe 2 operands from the register file, does something that probably is not the multiplication, the addition, the classic things that you think of, and produces a result and puts it back in the register file. It was not the only company. There was another company. The two were maybe the most aggressively pursuing this possibility. Another was Arc International, and Arc had this list that corresponds a bit to what you were saying before, but you see here a bit more in detail in this part in here, right? Some of the things that corresponds to these optional functional units, it's a different vendor and a different processor, but the fact that there are some instructions that may or may not be interesting, right? Like switch location at the top and bottom of 16-bit fields. Swap bits, right? It's something that is extremely costly to do in software. It's extremely easy to do in hardware, but maybe you don't need it, so why do you have, right? So if you need it, you can have it. If you don't need it, this instruction will not exist, right? And DSP functions, classic things that are useful, will come back to a number of things that are in this list next in 2 weeks when we will discuss design digital signal processors. This is a marketing slide, but it's interesting to see a bit the idea, right? Is what I said before, starting to get the performance without paying the price. Here you have a bunch of out-of-the-box processors, or processors that are not configurable, from Freescale, from PowerPC, probably from IBM or Motorola, I don't know, MIPS, ARM, and the Extensa Helix itself, but out of the box as it comes standard. And then you do a bunch of optimizations. You try to do the things correctly for the benchmark. I don't know what the benchmark was here, but some specific application. And you get something that is much more powerful. You see, it's significantly better than several versions of PowerPC. That is not a small or silly processor, but what you get is that you consume much less, and you go at a lower frequency than the frequency of the PowerPC to achieve actually a better result, right? This is one of the proofs, if you need one, that you don't need high frequency, or is not high frequency does not guarantee good performance. Is actually one of the components to get good performance, but absolutely not the only one, right? And you see also power very much. Again, this is a marketing slide, so don't take it as a scientific experiment, but it tells you the kind of idea and the fact that this idea can be made to work to at least some extent. In fact, in the same spirit, at the same time, practically all processors made for either FPGAs or for implementation in ASICs, right, in application-specific integrated circuits, in embedded situations where you manufacture a big circuit that includes, among other things, processors. All these processors targeting this started offering the possibility of both having parametric resources, as I was mentioning, or arbitrary functional units, or some ways to be very well, very tightly coupled coprocessors. One of the things is that at the time that people were doing this, and actually it's still true today, probably, I'm saying it in the past because it started at that time, but it's still there. All these tend to assume that you decide what are the parametric resources that you want. Do I want 16 registers or 32 or 64 for my application? That you take this decision manually. Manually means probably by simulating, by running some experiments and seeing what you can do. This, from a perspective of computer science, is actually a pity, right? And I was expecting something more to happen. Not much happened at the time, but I will bet that in the coming years, more and more of this will happen. Maybe today we will do it with more machine learning and so on. But the idea is to explore, to be able to explore the design space, right? So I have these processors that have a lot of knobs, that have the space for some basically VHDL, right? For some circuitry that I can add arbitrary circuit that I can add myself. I have on the other side a program that says, I want to do this. How can I get to the best result? And this was one tool that existed by Tensilica at the time, and that was part of what Tensilica will give you if you buy their, or if you license their processor. And you see here an example, is again a commercial example, so don't take it too seriously, but it's a beautiful example because it shows you the Pareto front. I hope you know what is a Pareto optimal point, right? It's a point that is better, at least in, so there is no other point actually. The definition will be that there is no other point that is better in both criteria. So you have two criteria here. You want to maximize performance or minimize, actually this is not performance, but it's time, right? Minimize runtime. You want to minimize the area in number of gates complexity. And so something is Pareto optimal is if there is not another point that is better in both respects, because if it is better, if it has better performance and it has better area, clearly this point is not good, this point is good and is interesting, right? So this is a Pareto optimal point. These are all Pareto optimal points here in these corners of this spline. They are Pareto optimal because, for instance, between these two, one is better in area, right? This is much smaller than this one, but this is much slower than this one. So one point is better in area, the other one is better in timing, and therefore they are all equally good in some sense. It depends on you, the user, to figure out what you want. So in this kind of design space exploration, when you have multiple goals like area and or performance, you are interested in these Pareto optimal points and to see how rich the space it is. And you see here that it is a rich space, right? You can go to extremely poor performance. I mean, it's not poor, it's right. It's three times worse than the next point, but it's extremely cheap, right? It's very, very small area. And then you can invest quite a bit of area, right? It's probably tens of times bigger than the smallest possible, but it is, in this case, 7 times faster. So it is interesting, right? Because this design space means you can invest transistors to reduce your performance. And you're reducing the performance not in every possible situation. This is very small, right? It's 30,000 gates. It means smaller than a little fragment of the alpha that we have seen at the beginning. But you get a very tangible improvement on a single application, right? This is one benchmark. You specify the application and you get this. Essentially, what people were arguing at the time, and I think it's still an important idea that is more used manually and yet not very strongly used automatically, and again, maybe machine learning will help developing this field a little bit more, is to do the optimization, do the computer architecture through retargetable compilers and simulators. That is, my processor and system are not fixed. I can change, is exactly what I'm describing here, right? I can change some parameters, modify, turn some knobs, or add little pieces of hardware here and there. And I need to have a compiler that understands this change of knobs, right? That understands you. You can imagine for the registers, it's easy to make a retargetable compiler, a compiler that understands how to create good code for 16 registers or for 32 and for 64. This is easy, right? It's sort of is the same algorithm that has a different number of registers. It's less difficult, it's less easy if I have for instance, I don't know, new instructions, right? The new instructions that didn't exist, and I have to tell the compiler, try to use this instruction if you can. This may be a problem that is very difficult in some cases. So you need to have this technology to create a retargetable compiler. These were the times that GCC was actually emerging as one of the best compilers, right? And people were doing research or starting research in the LLVM that, if you know a bit compilers, is very much used to do experiments in that domain. And they are essentially fundamentally retargetable compilers. You need a retargetable simulator, which is actually easy if you think about it, but is not easy to make it fast, and you want it to simulate very quickly new architectures. And you use them in a loop, right? You sort of decide to change the description, you generate a compiler and simulator, you compile the code, you simulate it, you get some information, and you change things, right? And again, this is something that you would like to have automated. You want to use this essentially to synthesize your processor and your system as a function of the application that you have here. Again, this is application-driven computing, right? Is embedded computing, is computing where you're not creating a general purpose laptop for anyone to use, but you're trying to create a system that is devoted to a specific application. The code that is in my SLR camera that does a huge amount of pre-processing, post-processing to the results, and wants to do it extremely fast, but I want it to do hundreds or thousands of photos with the same battery, right? So this is the kind of situation. It's a beautiful place, and it's a beautiful place where I think more research could be done, and I think something will happen in the past, because it's a confluence between computer architecture that has always been done traditionally by hand. If you read some of the papers that are part of this course, if you've followed other courses in computer architecture, it tends to be a place where people say, oh, this is a great intuition, let me twist simulator and compiler and so on, let me see what comes out, let me simulate everything, great, my idea was great, right? Maybe I do a couple of iterations, and this is my paper, this is my idea, this moves on to the next level. So very much not exploration automation, and this is a place where computer architecture means electronic design automation, right? Going algorithmically, trying to do a way to algorithmically get the best solution possible given a set of inputs. So in that spirit, actually, I was hoping that something would happen, because Tensilica actually went sort of down, but was bought for a reasonable amount of cash by Cadence. And then actually before, in an indirect way, ARC was acquired by a company in EDA that was called Virage Logic, but then Virage Logic was bought by Synopsys. And so here comes that the two biggest players, there are three big players in EDA, in design automation, are Cadence, Synopsys, and Mentor. Here it comes that two of the biggest acquire very strong processors, customizable presence. Unfortunately, not much happened in the process of customization, but I think is an area that is very interesting. And one area that I want to discuss with you a little bit, because I think it's very promising, and in fact, a lot of this is done constantly and since ever, but manually, and very little is done automatically, is introduce extension to an instruction set, right? It's exactly the problem that we already discussed before, is that I add a functional unit that is not doing the classic ALU integer or floating point operations, but something else. And it's something that you can do, and actually today, maybe not 20 years ago, but today, every commercial processor for ASIC or for FPGA gives you as a possibility. You can add easily one of these, right? The question is, what is the functionality that you want this special functional unit to have, right? The idea is what you want to do there is collapse there a number of different operations that you would have done. I hope you understand immediately what I mean in this left picture, because we'll have many of these pictures today and next week. It's essentially a data flow graph, a part of the intermediate representation of a compiler, if you want, where each node represents a different operation. You see it here, right? And edges of this graph represent the dependencies, represent data that move from one to the other. And what you want to do, so this is what the way the compiler will look at this code to be compiled, and will probably issue a number of instructions like an AND, a square root if it exists, or a square, I don't know what is this one, a plus, and so on and so forth, an addition, and all these operations. But the idea here is to sort of collapse all these things into a single function, right? A single three-input function, and call it with a single name, right? Is a single opcode, is a single instruction that corresponds to a specific functional unit that I put in my data path, so that whenever I need to do all this, I get this instead. Now, one of the questions there is, why do I gain, right? Why is this a great idea? Why, if I do a single instruction that does whatever my previous, sorry, let me go back, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 instructions would have done, why do I expect this one instructions to be significantly better than this 10? Yes, it's one, right? But it will be a much more complicated one, right? So why there is any expectation that doing this helps? And it's a little too easy, especially for people that like hardware, that tend to do hardware. There is this feeling that, okay, hardware is better, right? Software is extremely inefficient and so on, but hardware is good. It's sort of true, but it's not always so clear why. So I want to carry you through an example. It's going to be a semi-longish example, but I think it's useful for us to getting a sense of where we can gain through hardware instead of software. What are the things that software will never be able to access in terms of optimization? So I'll do it with an example that is a very silly example, as usual for examples, right? It's very simple, which is the code that you see here on the left. I don't know if it is good or bad C code, but it's probably correct. And I'll let you a second, actually. Maybe I do one of my pauses to stop for a second so that you think about it, what it is. It will give you also the time to be a bit more accustomed to this piece of code that we are going to use for the next several minutes, right? So let's do the little pause. So what is this piece of code? It's a little hidden because of the way it has been written, which is a little horrible, is just to minimize the number of variables, hoping that this minimizes also the number of registers that the processor uses and reduces a little bit the number of operations. So it's actually a little bit more tricky than it could be. I think, I don't remember exactly, but I think I took this piece of code, maybe with minor modifications from some software library. This is the code for doing an integer multiplication. In the specific case, is an 8-bit times 8-bit, resulting in 16-bit result of, again, an integer multiplication. The parts that gives it away, hopefully, is that you test 1 bit, right? This is testing 1 bit because 8,000 is only the highest bit of these 16 that is at 1. So it tests 1 bit of A, and depending on that, it shifts A in any case, and maybe adds B. So A gets shifted every cycle, and depending on what happens of 1 bit of A, we add B or not, right? So if you think multiplication, this is multiplication. Now, unfortunately, what is a little bit annoying in this, in understanding the functionality, is that A contains the result, the product, and the operand at the same time. Again, this is an optimization that, if you think long enough, you'll see that it removes a few instructions to make it efficient. So actually, this is an efficient software implementation of this functionality, but makes it a little bit clumsy because this A is 2 things at the same time, but different bits of A can only be one part, the operand, and the other the result, and we save some operations. All right, so okay, that's what I just said. Okay, so we want to do this, or we want to understand how doing this software compares to having a piece of hardware. Or actually, maybe let's look at it a different way. We want to look at this software and say, this is my application. I want, without knowing what I'm doing exactly, but I want to create hardware for this application and see how successful I am in doing a better job. So the first thing that I can do is one of the compiler things that we have seen in the past. I think we have seen it speaking of VLIWs, but we also mentioned that is important and useful in other contexts, is predication, is if conversion, right? I have an if then else here, and now I don't have it anymore. What is the magic? Is a little bit of the magic, right? It transforms this control dependence, the if then else, into data dependence. It creates a predicate, and it uses this predicate to obtain, to condition the assignment or the exact assignment to A. If you remember, there was an example that was in the, I think in the VLIW lecture, where I was telling you, you can do also predication in software. Normally, it's something that you should do using a processor that has hardware support for predication. You have seen, I think by now, because I don't remember when is the deadline, in fact, of the homework number 2, but it's part of what you see very clearly in Itanium. But you can do it also in software, right? You can do, and there was an example a bit like this, where you have this P1 that is a predicate mask, right? It can only be, if you think long enough, it can only be 0 or -1, so it can be either 0 or all ones, all the bits of my 32-bit register, and then I use it to bitwise AND B, in the sense that if P1 is 0, then this term is 0. If P1 is -1, or in 2's complement, all ones, this term is B. So this means take A, shift it by 1, and add either 0 or B, which is exactly what we had here, right? So I hope you are convinced that it's the same thing. Either add B or add absolutely nothing, right? Other than that, the code is exactly the same. So let's see what is the result of this, right? So this is the view of this basic block, of this internal part of my loop, of my for, and this is the calculation that is done in there. Is again a DAG. Each node represents an operation, and edges represent dependencies. And now, if I do it in software, suppose that I have a relatively simple RISC processor, right? Normal pipeline, similar to MIPS or something like this. How long it will take? I don't care about the initialization of the pipeline and the outside and the deinitialization, because these are details that will disappear in the big picture. What matters is how long I stay in the execution stage, and how much dependencies kill me. So imagine a pipeline a bit like MIPS, that is the simplest pipeline that you can consider. Imagine that I have all the forwarding paths. If I have forwarding paths, basically I do this in one cycle, I do this in one cycle, I do this in one cycle, and so on and so forth. So essentially I need one cycle, one execute cycle for each of these operations. So more or less, the length of my loop is about 6 cycles. Good. Now the question is, what happens of this in hardware, right? If I try to do this as a piece of VHDL, right? I have 2 inputs that will come from maybe the register file, will go back somewhere again in the register file, and all this is not a piece of code, but is a circuit, right? With my maybe 32 bits or whatever it is here. All right, so this is something that I always enjoy doing in person with you in the class, because I'm always amused to how long it takes to you or to your colleagues, I don't know, to you individually, but to your colleagues, to find the correct answer. The answer to what? I want to understand how complex is this, and how long it will probably take to complete this, how many cycles or how much time to go through this circuit. And to do that, I want to start to ask you a question, right? Here there is an operation. I have A, I have a constant, and I'm doing an AND. And what I want to know is, how complicated is this operator, right? Actually, what I want to know from you is a very precise answer, which is, how many transistors do I need? Because from the transistors, I can look at the critical path, and from the critical path, I can figure out the timing, right, of this operator. So you are going to tell me that I speak transistors. I should not, because this is a computer science department. So I'll tell you that a NAND gate, if you don't know, has 4 transistors. And I also tell you that I don't care if it is an AND or an AND, because generally when I'm doing a circuit, if I have a negation here, I don't compute exactly the AND, but the NAND of the input, I usually can compensate it later, because I hope you remember things like the Morgan theorem and so on. You can play around with inversions and sort of absorb them in the computation. So I don't care if this is AND or NAND. What I want to know is how many transistors I need to implement this function, and maybe already a sense of what is the critical path, how many transistors are on the critical path. I cannot resist, we'll make a break, and I think we'll make a few pauses in the following so that you have the time to think. Maybe because of the pauses in the video, if you really take them, you'll be more able to find immediately the solution that usually escapes when we do this interactively. So pause. How many transistors? How many transistors then for this operator here? Let's think, right? And so I have to do A, all the bits of A. So it's a bit width operator, right? This, I hope it is absolutely clear. So in principle, the answer will be, I need to do an AND or NAND, we don't care, per bit. I have 32 bits, I have 4 transistors per bit. So the first not wrong answer will be 32 times 4, right? But then let's look a little bit more closely, right? Each of these bits is ended by a bit that comes from this operand. And the bits here are either zeros or 1. Now, what happens if I take a bit of this and I end it with a 0? I know the result is 0. So do I need to put for this any transistor? Actually not, right? Because I need to take this bit, the bit that is like the bit number 0, right? That is for which this constant has a 0. I need to put it to the value 0, because it will always be 0, whatever is the value of A. So for that bit, there is no transistor at all. The same is true for any other bit that is 0 here, which are, I think, 31 of these 32 bits. And then I have a 1, right, here in the, to make the 8, right, in the 15th position, right? So in the 15th position here, I have a 1, and I have a bit, the 15th bit of A, with the 15th bit, with this 1, that are ANDed. So what is the result if I AND the 15th bit of this with 1? But the result is the value of the 15th bit of A. So do I need transistors for that? No, I need only to connect this bit here. So you see what happens, right? There are 0 transistors to do this. And to a first degree of analysis, there is 0 time, right? If wires metal is super fast, which is usually, right, again, at the first level of analysis, what this thing means is take 1 bit of A and connect it to these 32 bits, and all the other bits, put them to 0. Okay? Great. Now I continue, right? Now I continue and I ask you, how many bits, how many transistors to do this? I'm not going to tell you exactly how complicated it is to do a barrel shifter, right? A shifter that shifts of an arbitrary number. But I think you're starting to see the idea, right? So I'll do a pause again. Maybe I'll not do it. Maybe I'll do it again. So, but anyway, let me do a pause now and think for it for a second. It may be easier now. So how many transistors for doing this shift right? Again, it's the same game, right? I have to make use of the fact that I'm shifting by 15 bits. So when I'm shifting by 15 bits, there is no shift to be done, right? I need to take whatever was here, bit 15 in this, and I connect it to bit 0 here. Whatever was bit 16, I connect to bit 1, bit 17 to bit 2, and so on, right? So as soon as I'm shifting by a constant, there is no real shifting involved, but a different connectivity between input and output. Okay? So this is again something that contains 0 transistors and that takes 0 time at the first level of analysis. It's just a wire. Okay, last one, and then I'll not do poses anymore, at least not for some time. Now I have a unary minus, that is an inversion, changing the sign of the operand. So I have an operand here of 32 bits, and I want to change the sign. So is this a simple operation? Generally speaking, not, right? How do you implement? I spare you the pose here, but think about it for a second, right? How do you do from 5 to -5 in complement, in 2's complement? Well, you have to buy yourself a subtractor, right? You have to subtract 5 plus 5 from 0, and then you have -5. And this is the operation that you need to do here. So generally speaking, this is nothing different from an addition or a subtraction, sort of that kind of operator, right? So a bunch of transistors, and if you want to be fast, is actually a lot of transistors to make it efficient. But here in a special situation, and so once more, here is my pose. Isn't this a situation where we have less transistors for doing this because of the special situations we are in? Pose. What is special here? What is the peculiarity that helps us here? Well, if I look carefully to the input, and if I remember what we said before, we said here there is only one bit of A, the bit number 15 of A, that arrives here. Here I'm connecting this bit to bit 0, right? So bit 0 is either 0 or 1. So whatever and all the other bits are by construction to 0. And now in here, I have either one bit, even a 0 or a 1 that enters this minus. And so the result can only be 0 if the input is 0, or -1. And -1 in 2's complement, which I suppose is the representation here, because it was a program in C, so it assumes 2's complement. In here, I have ones in all positions of my word, 32 times 1. So now let's think. I have here 0 that enters, all the bits are 0. I have 1 that enters, all the bits are 1. So I don't need any transistor to do that, right? I need to connect this bit here, which is the same thing as saying the bit 15 that was here, and connect it to all the 32 bits of this bus, of this signal. So you see what is happening, right? In here, there is absolutely not a single transistor. I'll spend, again, 0 time to do these operations because of the nature of the operations, because of the nature of the constants. The same is true here, right? There are 0 transistors to do this shift because of the same thing that we said before. It's just a connection of A0 that is connected to A1, A1 connected to bit 2, and so on and so forth. The only things that we really need to do here are this one. Can I say something about this? Well, not really, right? Because here I have every bit that can be either 0 or 1. Here, every bit that can be either 0 or 1. It doesn't help the fact that these are either all 0 or all 1s, because this is a bitwise operation, right? So each gate is absolutely independent from the other. So the fact that there is a huge correlation between the different bits of this one does not help to simplify. So this is like we said at the beginning for that one, 32 times for transistors. So this is a little component, and this is a normal addition. But so how long does it take to go through this if I do a circuit and I'm in the same technology that was used for my processor? Well, I need exactly one cycle here because it's exactly the same reason why I needed a cycle in the software version. And I need a little bit more here. It's a very little bit more, right? Because this is an operation that is 01, doesn't depend on a number of bits that I have, right? So it's either 1 or 2 cycles that I have to spend for this and nothing else here. So it is between 3 and 6 times faster than it used to be in software, which gives rise to an idea, which is exactly the kind of idea that we are pursuing here, which is to say, why don't I put a new special function on the side of the ALU and whatever else there is on my register file of my standard processor. So imagine this is the standard processor represented in a peculiar way. I put in parallel this special instruction, I call it mstep, whatever it is. It does a functionality that is exactly what is specified here. And if I use it, I will get this benefit. I will get reduced by to 1/3 or to 1/6 the time that I need to do this operation, this software application. And I can continue. I can continue by noticing that what my problem is, like it was here, is that I have control flow and I don't know exactly how to handle control flow. So I want to transform control flow in data flow so that I can do this kind of data path of these circuits. And I want to continue, and I want to use what we have learned, right? We have learned this unrolling when we were trying to do big basic blocks and big data flows in very long instruction word processors. Now I can use the same ideas, right? I can continue with the same techniques and get rid of the loop. In this case, it's very easy because it's actually 8 iterations. And since it is 8 iterations, I can unroll completely, full unrolling, and then I don't have the loop anymore. And now if I look at this program, that is still the program that I had at the beginning functionally, but it's completely different because there is zero control flow. It's just data flow. And is this horrible thing that now becomes a little too big for me to represent, but is essentially the same thing that we had before many times, right? Once here, once here, once here. Now, how much time does it take in software to execute this? It has actually improved a little bit in ways that we have not measured because we didn't in the past really look at how much the control flow, the branch of the for loop will take. But essentially here what I have is something like the same 6 operations 8 times, so something around 50 cycles to execute. Now, let's think of the hardware here, right? And maybe it helps if I redraw this by taking away a lot of details. What essentially we are doing here is, remember that this one here is just a wire, right? You remember that because it is connecting the bits in a slightly different way, not 0 to 0, but 0 to 1, 1 to 2, and so on, but is wires, right? And this is wires, and this is wires, and so on. And so if I look at it carefully, what I have here is a path from A to the plus, then to another plus, then to another plus, and so on. So essentially what I have is essentially this, right? A and B that have some ends, these ends, you remember again from before, really stay, so these ends are there. Maybe not exactly in this way, but more or less yes. And more importantly, this chain of additions. Now, how do we implement this? Okay, so this is suppose that there are some details that are not visible in this succinct version, but basically we can do VHDL of this and implement it and do hardware. Now, one of the questions is, can I do better, right? When I'm doing this, this circuit that I see here, can I do a better circuit? And this is another place where I cannot resist by doing a pause, because there are at least a couple of things, a couple of improvements that you can do. I think everybody can and should be doing a first improvement of this circuit, right? Rewrite this circuit in a way that is better. And then there is a second one that maybe some of you don't know, but I will come to that in a minute, and hopefully maybe some of you do know also the second one. The first improvement I already drawn here, and is the one that I think everybody of you should have seen, is the implementation of this chain of additions by taking advantage of associativity, right? Addition, these are not floating point additions, these are integer additions, so they are perfectly associative, like they are in real numbers or in integer numbers. Therefore, because associativity is valid, you can restructure this addition in any other way, in any other associative way that you want. And I've drawn it here manually because unfortunately I'm not on a tablet, so it's very painful to draw, so I spared you the pain of seeing me trying to do this. But you see here the idea, right? You try to do it as much as you can in parallel. If I can get back my laser pointer, you can do it, you try to do it as much as you can in parallel, and you do sort of 2 by 2 a reduction until you get to the final result. This is something that everybody of you should have thought, right? It's a normal thing that you do in every situation where you want essentially to exploit parallelism. What you do here is there is no parallelism, you have to do everything sequentially, and here you're doing the first 4, in this case it's exactly 4, right? The first 4 in parallel, then the second 2 in parallel, and then parallelism fades out, but you have the results, right? It's a very important optimization in terms of time, because instead of having something that is in linear time, this is O, the number of additions, so is ON. This is O log of n, right? The number of steps here is the logarithm of 8 in base 2, so is 3. There is another way that you can improve on this circuitry by using another property, and this is maybe the way that you possibly did not imagine or do not know of, which consists in doing essentially the same operation, the same conversion into a binary tree that we have just seen, but actually doing it with a different type of adders. And there is an adder that is called a carry save adder. That is a very funny type of adder because it takes 3 words to add and returns 2 words whose addition is the same value as the addition of the first 3. So I repeat, or let me compare it with a normal adder. In a normal adder, I have 2 values that enter and 1 value at the end, and the value at the output is the sum of the 2 that enter. Now, this carry save adder has 3 inputs and 2 outputs, but the sum of the 3 inputs and the sum of the 2 outputs is the same. So if you think about it, it's an adder, right? Because you had 3 things to add, now you have only 2 things to add. So you've added one operand to add has disappeared. A bit like in a normal adder, you have 2 things to add, you now have only one, so basically you are done. You have reduced by one the number of things to add. So you understand that in some sense, they do exactly the same job, right? They remove one addendum, except that the carry save adder can be done in O1. It doesn't depend on the number of bits. Whereas any other adder is O something, typically maybe log n in the best cases, where n is the number of bits. So it's amazing, right? Because if you think about it, one of them doesn't depend on the number of bits that you have in the word. The other one depends on the number of bits that you have in the word, but both of them do essentially the same function, reduced by one the number of addenda that you have to add. And here you have 8 addenda that you have to add. So for 7 times, you can use one of those carry save adders to do the addition. And so you can do it extremely efficiently, and you can do it in more or less a binary structure like we have just seen. Only at the end, you'll find yourself with 2 results, and for adding the last 2 addenda, carry save adder is useless. So you need to buy yourself a normal adder. So this means that if you do some tricks in arithmetic, what you have is a network of additions that are these. A bunch of these carry save adders. You can go on Wiki if you want, if you are curious. Of course, it's not terribly important for the course, but it's good to know that these things exist. And this network of carry save adders is here called column compressor, because this is how people call it, but it doesn't matter, is this tree that is here. And then finally, there is one normal adder. Okay, so the question is, if we understand this, right, how long, we don't understand very well what is in here, but it's not important. I'll tell you something in a minute. But the question is, how long is this operation, which corresponds to implement this piece of hardware, which is a simplified representation of what we are interested to implement in hardware. So again, the software, we said it already, right? It's around 50 cycles, this thing. It's no surprise. Now, let's look at what we have here, right? We have a bunch of ends in parallel, right? They are all in parallel, right? Like these. So essentially is almost nothing. We have an addition, which is essentially one cycle. And here's something that is simpler, we know in this case, is simpler than 2 levels of addition because of the example, because of the first optimization that we have done, but is actually much better. So it's something that in the very worst case, in fact, is probably absolutely not 4 cycles, but in the worst case, it's 3-4 cycles. It's more likely 2-3, maybe even 2 instead of 3, okay? So it's much, much shorter, and that's exactly what happens, right? So from 50 cycles, now I go down to, say, 3 cycles. So something like, again, a factor maybe 15. And so automatically I think, why don't I put a special strange functional unit here that does this functionality implemented in the best possible way, but it's just a question of implementing. I didn't change anything, right? It's just I did it a bit better. And I will gain in execution time a factor 10, 15. Now, what are we saying? We are saying, in a sense, a stupidity in the specific case that I chose. That what I chose here turned out to be a multiplier. So everybody knows this, right? I want to have a multiplier here. I want this special piece of hardware. And if you take, for instance, NIOS, one of these customizable processors that are meant for FPGAs, you have in the compilation, in the configuration windows inside the tool, you can say, I want to do multiplication in software, which essentially gives you the code from the beginning. It's very well possible that actually that piece of code I have taken from their library, because then there will be a library in the Altera iOS that implements it in software. Or I implement this operation, or I implement this operation, which is a normal multiplication, and this one is the intermediate. It's exactly what we have seen. The point of this exercise, and I hope that it's valuable for you to spend the time, to have spent this time, is to understand, why do I gain? Why it is better to have a mule in hardware with respect to do it in software, right? I mean, everybody gives this for granted, but two things I think are to remember here. Why do I gain? Because I have new ways to exploit constants, because I have new way to represent operations, or different ways to do operations where I restructure this tree, this addition tree, in different ways where I gain very significantly. I even change the complexity of the operator to be from O log m number of bits to O1, independent from the number of bits. That seems even a joke, right? That you can change the complexity, but this happens when you play hardware games. So this is the first thing to understand. There are in hardware things that you can do that make things significantly better. And the second thing, the second takeaway here is to say, did I do something that was using the fact that I'm doing a multiplication? Absolutely not, right? I just looked at this and I tried to exploit what I was seeing here, right? Remember the kind of discussions that we had around this first graph and about what is wiring. I didn't use the fact that this was a piece of a multiplier, right? I ignored it. I just noticed that there are operations that, if I try to do it, simplify. In fact, if you give this VHDL literally of this computation to Vivado or to Synopsys Design Compiler or to any other logic synthesizer, the fact that this is only wiring is going to be found out completely automatically without you doing anything. And so the second takeaway is that not only I gain by doing hardware, but I could do this absolutely automatically. I can do it for anything, not only for mule, where it is pretty silly because we all know that it's good to have a multiplier, but for anything that is a piece of software that comes in. So one of the takeaway that I want to have is this: why hardware is better, right? Because we are going to use it also next week when we talk of high-level synthesis, or maybe we don't use it, but I mean, it's the motivation for doing all the high-level synthesis, right? And here are some of the examples, some of the things we have said, some we haven't. One is that we do parallelism. Actually, we have said when we have transformed into this binary tree of adders, right? We do things in parallel, right? We do things in parallel. In that case, we were doing several addition, 4 addition, if you remember, in parallel. Whereas if you do normal software, some people call it temporal computing, in the sense that it is you use your ALU that does additions over and over in time. So in time, you spend time, here you spend hardware to do parallelism. But this is a very cheap form of parallelism, right? It's not the parallelism that we have seen at the beginning of the course, where we start reordering instructions, doing reorder buffers, and so on. Here is a very cheap kind of parallelism. In our example, I just implement this part here with some parallelism, things that can happen in parallel just by doing my circuit in parallel, right? There is no additional hardware that I need to support if I compare this with my out-of-order processor. Of course, I'm doing only one specific function. I don't do anything I want here. I do only a very specific function. But again, that's part of the game. Another element that we probably never evoked, and the example before did not cover, but is good to take into account, is the fact that processors are synchronous circuits, right? They use a clock to synchronize everything, and we have everything counted in cycles, right? And we decide that in the cycle we do something, right? And when we do pipelining, we decide basically what is the ratio, what is the relation between some of the most complex operations that we have, suppose a multiplication or a multiply and accumulate, and a cycle. Right. For instance, take this only as an example. It doesn't mean that it has to be the same everywhere. But in this case, we have decided, for instance, whoever has done this processor has decided that basically the multiply accumulate and the multiply that are essentially the same length take one cycle. Right. Sort of the relation between cycle and multiplication is this one. Just to be clear, I could have chosen, for instance, to have a clock that is twice as fast and multiplication takes 2 cycles, and instead of going at 1 gigahertz, maybe it will go at 2 gigahertz, right? So this is a choice, it's not important. But whatever choice I make, I always have operations that are very different, of very different complexity, right? And the complexity in terms of time taken to really execute the operation is probably even underplayed here, right? And is extremely fast. I go through 2 transistors. The critical path is 2 transistors. Add is hundreds or thousands of transistors. So it's much longer, and multiplier is tens or hundreds of thousands of transistors. So the length of the individual instruction is very difficult and different. And whatever I choose as a clock cycle, suppose this is for the Mac, the other operations may finish much faster, but since this is one cycle, also the end will be one cycle. Also the shift right will be one cycle, and so on, right? I will not be able to take advantage of the fact that within this cycle, actually the operation has finished very early in the cycle. I will just wait and then at the end of the cycle put in. It's the game of synchronous logic, right? Because I have a synchronous processor, I'm not waiting for it to be finished. I decided that everything has to fit this cycle. As soon as I try to do special functional units, I'm actually creating more complex functional units, more complex pieces of logic. And now, if I put these 3 operations into the same operation, now I do them maybe sequentially, but they still fit a single cycle. So I don't quantize. Quantize means seal off, right, in math, right? Sort of the integer. If this takes 0.1 cycles, in practice for me will take 1 cycle, the seal off it, right? The minimum integer that is bigger than 0.1, which is this take 1 cycle. So I have to quantize to the next integer in software, but when I do hardware, I just put one after the other. And if this is 0.1 and this is 0.2, they do 0.3, which is the seal of 0.3 is still 1, so it still takes 1 cycle. Right? And here the example is maybe 0.1, 0.2, and 0.3. If I put together is 0.6, and the 0.6 is still 1. I hope you understand the idea, right? We have seen the games with constants. As soon as there are constants, hardware may become easier. There is one thing that has been exploited also in compiler, but these days that doesn't pay off very much because processors and hardware has become so cheap that processors all have multipliers and so on. But for instance, if I have to do a multiplication by 5, there is an operation, I think it's called in compiler technology, it was called, when it was done, strength reduction. I implement an operation of a high strength, like multiplication, with something that has lower strength or lower complexity, which are two operations here, where I do shift A by 2, I get 4 times A, plus A, I get 5 times A, which is exactly what I wanted, right? And while this may not, so the moment I have each operation that takes one cycle in execution anyway, this takes one cycle, this takes 2 cycles, so it's a bad idea, right? That's why today is a bad idea in modern hardware. But if I do hardware, if I do a circuit, this is a multiplier, is a big unit. This is shifting by 2 is the usual story, that is actually only wires and is an addition. So basically, instead of doing a multiplication, I do a single addition and is the same result. So this is great when I do hardware, and again, is useless these days when I do software. So it's another advantage. Another advantage of doing hardware is that in software, if I have a 32-bit multiplier and it takes one cycle, that's it. If I need to multiply 3 bits by 3 bits, it takes one cycle, because that's the multiplier I have, and it doesn't even make any sense that I put smaller multiplier in my architecture, because in any case it will take one cycle. Now, if I look at my code and I discover that something has a smaller number of bits really needed, right? In here I figure out, because there is a piece of code, I can do it automatically, and this piece of code clearly restrict the range of index to something that is smaller than 128 and has only 7 bits. Now, if I have 7 bits and I'm doing hardware and not software, if I have to multiply these 7 bits by something, I can put a 7-bit multiplier instead of a 32-bit, and it will be much cheaper because it will be much smaller and it will be much faster, right? So this is another advantage that I get in hardware and I don't. And the arithmetic optimizations is the example that I was giving you before, was a good example of arithmetic optimization, where I change an adder or a bunch of adders with a bunch of carry save adders that are components that have a different number representation somehow. It's one way of looking at it. And they are game changers, right? The big O complexity changes. And this means something that seems, almost magic, right? It's not magic at all. It's possible because it's a different representation. But that's what people do. So for instance, why are floating point units much faster than libraries that do floating point? For all the reasons that we have seen so far, including the fact that typically I convert from maybe the IEEE representation that I have to obey in the processor into some other representation that is more convenient for doing hardware operations. I'll do all the hardware operation in extremely more efficient ways because of my choice of representation. And then if I need to give you a result in IEEE representation, I go back in the IEEE representation. And this gives me a huge lot of possibilities to increase my efficiency. And are things that makes no sense. Whatever I'm saying doesn't make any sense in software optimization, but in hardware is the bread and butter of optimization. Okay, so this is basically a little repeat of the same things on the example that we had before, and looking at what is the critical path. So if you understand all this, so what again is the takeaway? We have the possibility of doing hardware. If we do hardware for a special functional unit, for a special instruction, this hardware may be extremely more efficient, and we can do all this essentially automatically. It's just analysis on what we are implementing in hardware so that we implement it well. So what one would want to do is also to formulate this as an optimization problem that says, okay, give me your application in C. Let me zoom in And let me try to find the biggest part that I can take so that I convert this into hardware. I put them as a functional unit of my processor. And whenever you give me that program, instead of going and resorting to the normal functional units, I do it on this special functional unit. Again, essentially the idea of the multiplier that we developed, but not for the multiplier that we know is necessary, but for something completely strange and bizarre that I don't even know what it is, right? So people have been trying to do this. Actually, this was a startup that we had here at EPFL, but there were many, many other people that were trying to do the same things around us, and basically bringing functional unit, application-specific functional unit from high-level code. You write C code, I'll tell you what to put into your processor to accelerate. Does it work? Yes, it works. And you see here, again, the orientation is slightly different because this is speed up, but it's a bit like the Tensilica slide that I showed before, the design space. These are all Pareto points, are all optimal points in some sense. If you invest more area, here it is a logarithmic scale, what is the speed up that you get? And you see that you have a lot of potential, right? You go from 2,000 gates to 30,000, so maybe 10, 15 times more, but you get an application speed up of a factor 4 to 10, whatever it is, 2.5, 3, right? Which is a significant improvement for a relatively small investment in gates. And you see here on a number of different applications. And again, keep in mind, right, what we are doing here, what these points are doing for DES are completely useless for autocore, right? These are completely orthogonal enhancement of a processor where I add instructions for one application, but most likely, more likely than not, they are useless for any other application. But if I am interested in that application and not in something else, that's good enough, right? So this is something that has a bit disappeared. Actually, processor customization, non-automated, is the most widespread method to design efficient embedded hardware. If you go and look, it turns out that, I don't know, probably in this microphone, active microphone that I'm using in this lecture that I buy from Logitech, probably in the chip inside that does this active amplification and filtering, it's very likely that there is one of these ARC International processors that now belong to Synopsys, because they are extremely specialized by creating manually a number of instructions for audio processing. So there are processors that are extremely good for audio processing by having the right set of instructions. They are not as clumsy as maybe the ones that I was showing in some of the slides before, but they are devoted to at least an application domain, right? So every processor is somehow customized this way these days, especially in the embedded world. Automation is little, and it's a pity. Some people will come back to this later on, but some people call this the fourth generation of HLS, because in a sense, this is a form of, if you want, HLS, right? High-level synthesis. I synthesize a system by putting there a processor, right? I start from code, and I do generate some hardware by putting there a processor, and by deciding what shall I put around this processor in such a way that it has the highest possible performance given a relatively restricted budget of transistors and power. It's very nice in one sense, because it builds on everything that we have seen, right? Processors, maybe simple processors and so on, and adds only things that are data paths, right? These pieces of computational hardware that are fairly easy to optimize, and so it works very well for very little effort. One of the cons that we'll be discussing a little later is that the parallelism that we can exploit is only within what can be converted to data flow, that is not control flow. So this may be a limitation here, but is one first step in the direction of doing high-level synthesis. We're going now to look at more conventional ways of doing high-level synthesis. And actually, this chapter number 2 of this lecture is about the most classic high-level synthesis that you know. If you have ever used Vivado HLS, and you will anyway for the homework number 3, you'll find in here this chapter will cover how essentially Vivado HLS works. High-level synthesis is this idea of creating circuits from a software for a programming specification. And let's assume that for the rest of the day and the course, that this is C, C++. So the idea is to replace essentially what Verilog and VHDL represent. They are RTL, register transfer level languages, where essentially you place down registers and place clouds of combinational logic in between them. And you do this almost explicitly, right? If you have ever used VHDL, you know that to write a flip-flop or a latch, you have some very specific construct, and then you write all the operations. If you have been with me in the bachelor, you probably have heard me saying, don't even start writing a piece of VHDL without having drawn the circuit. You have to design completely the circuit yourself, and then it's just a way to put it in writing and get a synthesizer to do for you all the optimizations. But essentially, the circuit is designed by you. Here, the idea is to move up, right? To have something that says only functionality, that has no timing information. It says what is the input, what is the output, but not when things happen. And get the hardware done automatically for you. It's a very old idea, and in fact, there is a little bit of history in a very short paper that is on the web that you can find in Moodle, and I think it makes an interesting reading also to see a bit how things develop sometimes in industry and in the world in research. It's an idea that is almost as old as processors and circuit design, but is actually something that was very developed in the 80s, 90s. But it didn't go anywhere commercially, although actually some companies invested a lot in that, and somehow started to pick up in the early 2000s, and actually is pretty common now, but only in very specific context. And the context is the one of FPGAs. I'll come back to this a little bit later. Not much has changed in all this time. It's based basically on the same ideas that we are going to visit in this second part of this course. One of the problems of high-level synthesis that has always, in my opinion, hampered the development of the field and the reach that it could have is that the output of HLS is terribly ill-defined, right? I said before, it's something like, I want to go from C, C++ to a circuit that computes what this program was saying. But then you can say, and it's a sort of silly stupidity that I'm saying, but you could say, okay, I give you always the same system, processor based, and I compile it and I put this in the circuit as a sort of piece of firmware, and here it is. This is high level synthesis, right? Because I give you a piece of hardware that does exactly that functionality. Now, of course, nobody calls this high-level synthesis. Nobody means this high-level synthesis. But you see, it doesn't contradict the fact that you are getting hardware out of the program, and gives you a sense of how poorly defined what you want is. Somehow the informal expectation is that there is way more parallelism that your processor could do, right? That is where the trick is. Essentially, you want to play all those tricks that we also have seen previously in part 1 of this course, but somehow you need to formalize. So somehow it is usually formalized into some templates, which is actually never said very clearly, right? You can go into the manual of Vivado HLS. It will never tell you exactly what is the architectural template of what it constructs. But somehow, internally, these tools need to have some idea of what to do. And typically it's something like this, right? Something where you have a data path that contains all the units that you need to compute, to do the calculation that you need, a bunch of registers and of steering logic, that is multiplexer, right? Selection of inputs and outputs. And all these connected so that the memory gives things to the data path gives something back to the memory. And in parallel, a controller that tells all these people what to do, right? At which moment in time. So the clear major problem that you have is that you start from having a specification that comes from C of what you need to do, which is essentially, again, a data flow graph, a DAG, and you want to decide essentially two things. Who is going among my components that I have, or that I want to put down in this part of my circuit, is going to perform which of these operations that I have, and when I have to do these things. So one comment is that you may have seen some of these problems. One is the problem of to decide who does what is called the problem of binding. The problem of when to do things is the problem of scheduling. And you may have seen them if you have taken it in the course of Nanni De Micheli here. I think in the master he gives a good part actually of his course is on algorithms that are used for high-level synthesis, and are exactly the algorithms that we are discussing here. They are very old algorithms, very old in the sense that, again, they were developed in the 80s and 90s. What we are doing here is not duplicating what Nanni does. I will not look at things at that level of resolution. We'll see some examples of scheduling, but we'll not go into any of the actual algorithms. I'm looking at this from really the higher level, from an higher perspective, which is what can we do of this? How much do they help the programmer? Do we get the result that we expect or not from doing this job? If you look at what we are doing here, the first thing that you should be thinking of, hopefully, from the previous parts of the course, is that this looks remarkably like VLIW compilation, right? Somehow you have your 4 multipliers, you assign 1 multiplication to each, and then you schedule the addition on one of the others, and so on and so forth, right? There is a lot of similarity. There are also some differences that are important. One of the things is that you don't have a fixed number of resources. If you are in a VLIW, someone will come in and tell you, you have 1 multiplier to use, or you have 4 multipliers. And you see here an example, right, where you have 2 different schedules. This one needs 4 multipliers. This one can needs only one multiplier but takes one cycle more. So these two solutions are two absolutely legitimate solutions that trade off some time, one cycle more, for some area, 1/4 of the multipliers that I have in the other solution. This is something that, of course, doesn't exist in VLIWs because the resources are fixed. The other thing is that clock cycle is constrained but not fixed. I'll make an example in a minute and you'll understand, but it corresponds exactly to what we discussed before when we were thinking of why hardware is better, and I called it there the non-quantization of time, right? It's that problem that comes back again. So if it was not terribly clear in my explanation before, which I admit it's possible, maybe it will be more clear now with another example. There is no register file in here. There is something simpler that is essentially a subset, if you want, of the register file with the ad hoc connectivity. If I go back to this slide, imagine this as a register file. Essentially, what is a register file is 32 maybe, or whatever is the number of registers in parallel with one multiplexer per port that selects any one of the registers, right? This is what a register file is in practice. And what you have here is that you may have simplified this, right? You may know that here from this port of the memory, from this multiplexer, you always get only the first register and never anything else. So you do a multiplication was first operand is always R0, so to speak. So you remove the multiplexer and you just have a wire that goes here, right? So it's essentially what it means, this no register file here. The other things we are going to see a couple of examples. So these first two points, something in the first example. The first example is similar to also the one I made before, where there is this trade-off between the 4 multipliers and the one or the one multiplier. But here there is an intermediate case that is actually even more interesting, because here you schedule for 4 multipliers and you need 4 multipliers. Here you schedule for 2 multipliers and you get exactly the same timing, because you have some slack that you can use in these two operations. And therefore, this is simply better. If you want to go back to the definition of Pareto optimal, this is a solution that is Pareto dominant on this one, right? It has the same or better timing, the same in particular, and has the same or better area, better because it removes 2 multipliers. Now, these two schedules, if you had a 4 multiplier architecture in your VLIW, will be exactly equivalent, right? You will not care when you do it, but now you do care and you would like to achieve this schedule if you can, because it's actually simply better than this one. And this is something that has no immediate analogy in the VLIW world, right? In the VLIW world, you do either one depending on how many multipliers you have, and that's it. This is the example, the second example corresponding to what we call the no time quantization in the first part of this course, and is an example where basically you have quantized everything to a given unit, 1t, whatever is t, 1 nanosecond or whatever, and you have quantized everything in clock cycles. You need 2 clock cycles for doing a multiplication, because actually the hardware takes 1.4 clock cycles, but you go to the seal, and the same for the addition, which takes 0.6. And if you can rearrange these the quantization of time in a different form, you still need to quantize, but maybe you can change the period. You can take a period that is lower, a period that is 40% more than the period before, so the frequency has gone down, but the actual wall clock time, the time that actually you spend to do the calculation, is only 2 of these long cycles here, so 2.8t, instead of 4 of the shorter cycles here, that is 4t. So you're actually almost 35%, whatever it is, faster than before with a different clock by playing with the clock. And again, the motivation, the reason behind this is exactly the same that I was discussing before. So the only real maybe piece of progress that there has been in high-level synthesis in the last few years is this famous paper by Jason Kong and Jiru Zhang in 2006 that is essentially captures in a single formulation most, if not all, of these problems, especially these kind of problems that we have seen here, into a single formulation, and therefore constructs algorithmically a valid schedule with minimal latency. And this is built inside some of the tools today. I think my guess is that almost every tool now uses this formulation inside for the different optimizations, but definitely I know for a fact that Vivado HLS has. Now the question is this enough? So once I have done and solved all these problems, do I have something that I give a piece of C code and makes a reasonable piece of hardware out of it? And the way I want to tackle this, because I think it is the most instructive way and maybe the more fun way somehow, is to take a piece of code and try to apply what we understand as high-level synthesis. And I think we have a reasonable but understanding, but we will improve it by doing this exercise. See what comes out and figure out what to do next if we're not happy with the result, right? And the example I'm going to take is this finite impulse response filter, right? So one of the most classic filters that people want to do is very simple. I invite you to pause. I'll not do the pause officially, but I invite you to pause a little bit the video so that you get a little comfortable with this code. I hope everybody understand what a finite impulse response filter is basically this convolution with you convolve an input signal, which is X, with a fixed kernel that is C, a set of constants, and you produce a new signal, right? It's used in a lot of signal processing situations to do every sort of high pass, low pass filtering, and so on and so forth, depending on the shape of the kernel of the constant C. This is a super simple, ridiculously simple version with only 4 taps for constants. So it's very short. Typical real applications these days, I think, have 128 taps or something like this. And an example of something extremely simple is a very simple loop. Again, you have to read the details a little bit, and I invite you to do it before continuing, because it's good to have understood well all the little details of this code, but it's a very simple piece of code, and at the same time something that people care. Just to be clear on a few things before maybe you pause and try to understand, X is the inputs, right? So I call this, imagine this as a sort of a function where I come here with a new X every time, and I get Y, which is one sample of the output signal. So every time I bring a new X and I get Y, that is a new output point. And shift reg here is a sort of a static variable, what I think in C you can define as a static variable, meaning every time that you come back, shift reg 0, 1, 2, and 3 contain the same value than the last time that you visited. Okay, so I say that I will not do an official pause, but maybe I do an official pause it for a second and try to understand this piece of code so that it will be easier for you when we go on. The first thing that we can do with this piece of code is to make a literal translation using this idea that I outlined before of this sort of template where I put on one side all the pieces of storage that I need. Here are the pieces of storage that I need to contain shift reg 0, 1, 2, 3. Here is ACK, so essentially all the variables, the individual variables that I have in my program. And here I put on this side all the operators that I need already interconnected with whatever I need in each iteration to compute. You can see here things that I've done where I have taken x times c is one of the computation, x times c is here. Then I have here c times one of the other shift reg, which is here, and depending on which one I select, depends on the I and therefore on the iteration. I have done these in parallel, right? You see that they are in parallel because they are in if then else. So I have done if conversion. Once more, I hope you remember what it is. We have seen it long ago. I have basically predicated, if you want, this code in the sense that I do both, and then I select at the end which one I take, right? It's the same thing that we do in processors with predication. This multiplexer is controlled by this test on I. And so on and so forth. So you can look at the other details, but essentially this creates the a circuit, right? And this is a circuit that has our input here, which is X, and maybe is not marked, but basically this accumulation at some point will be Y, or Y is this one, is actually ACK, right? So it's here. So it is a circuit that computes Y as a function of X. Now, are we happy, right? The question is this one. This is the same circuit. I just redrawn it, right? So you can convince yourself if you go back and forth a bit between these two, but here there was this strange thing that was 0, comes back as 1, comes back as 2, comes back at 3, which is exactly what was written here, right? Every time I do this iteration, I do one of these transfers between these two registers. Now I just redrawn everything in a way that is a little bit more human to understand. You see again here the seed and the two multiplication. So it's exactly the same, right? I have made clear here that there is a controller that is the one that tells each of these when to activate, right? So are we happy, right? This was the question. And well, no, right? We are not happy because what we are doing is that we are doing in a sort of sequential way all the different things that we can do and we need to do. And this circuit, if you give it to Vivado HLS, by the way, all these results I think are literally true. If you put the code that is here in Vivado HLS, you get one of these execution schemes that you see, or timing diagrams that you see below. And of course, we are not happy because it is completely sequential. There is no difference between this and taking a processor, the worst processor that you have, and doing this. I hope you start seeing what is happening, right? Because this is already fairly similar to what was happening with VLIWs. Remember my first example in VLIWs that was a sort of almost comical outcome is that it was a very simple loop that we were passing through the scheduler, an intuitive scheduler. We didn't even give any algorithm. It was an as soon as possible scheduler, and the result was a disaster because there was zero parallelism, right? And this is exactly what happens here, right? If I don't do anything, I get nothing. And I get nothing for exactly the same reason, right? Think about it. I have here dependencies. I have an ACK that is computed, and then I need to go here, and I take ACK again. This is C, right? Is ACK equal ACK plus. So I need to take ACK. So there is a loop carry dependency. So I cannot do something before I finished before the other one, especially because of this structure of the loop. So I need to do something on the structure on the loop, on the refactoring and so on, so that I get the right result. And this is exactly what, if you go on a manual for Vivado HLS, they try to teach you to do. In fact, this example is very similar to that of a book that is written by several people, including one that was until recently the technical product manager of Vivado HLS. So this is exactly how they help you to write reasonable code. And this is one of the problems, right? You have HLS tools today that are still absolutely unable to abstract away hardware. In fact, what you need to do if you want to write C and get hardware is that you put C in, you look at the schedule, you say, oh my God, this is doing this type of hardware, which is a mistake. I know that I want a different type of hardware. Let me rewrite this in such a way that I get the hardware that I know is possible. Right? So it's not something that helps software programmers. It's not something that you say to a guy that until yesterday was doing Scala and has never seen a piece of hardware. Oh, you know you can write C and get fantastic hardware out. Is not gonna go this way. And these slides are meant to help you get a sense of this with a relatively complex or articulated example. So one of the first things that we can, so let's try to improve, right? Let's go back exactly where we were, unhappy, right, because of this result. And one of the things that first we can observe is that we know exactly, although there is this control decision, we know exactly what happens, right? For 3 times we do this, and once we do this, right, at the end. So it's not clear that, or on the other end, it's clear that we don't need this control decision. Somehow what we can do is to take out of this loop the one special case and put it outside of the loop, and now the loop has no test again. I hope you see what we are doing, and this name for this thing that we are doing rings a bell, because when we were looking at VLIWs, we were doing exactly this. We were looking at exactly these techniques, and actually there is nothing new in these techniques. When these techniques have been taken and started being used in this context, they were already existing for VLIW compilation. Unfortunately, you have, because of the same reason that we were discussing with VLIWs, that the space of how do I apply all these possible rules is too big, what you actually have to do is that you have to do it yourself. So this is manual loop peeling, right? You rewrite the code to write it this way. And if you write it this way, what the hardware that your HLS tool most likely generates is this one, which is slightly different in the sense that now, let me go back to see the difference, right? X is not sent into a different multiplier, but is actually sent into the same multiplexer that goes into only one multiplier, because you know that this multiplier is always multiplying C and either multiplying X or one of the other signals, but never both at the same time. So there is no need of the second multiplier. So this code, this data path is a little simpler, but you'll notice also that the schedule has not changed at all, right? One thing that we can observe is that in our code, our only loop has now essentially 2 parts in the body of the loop. The first one has no loop carried dependence, and the second one has a loop carry dependence, right? This goes through ACK. The other one doesn't have any dependence. So one of the things that can come to mind is to split the loop. And again, it's one operation that we know of because, again, it was in the long list of loop operations that we could do for VLIW, and it's called loop fission. We just splits the loop. Actually, I take also the last instruction of the loop and put it close by to the correct one. And we get something that doesn't change actually at all the hardware. Maybe it's predictable, right? Because essentially it is the same operations, it's just written in a slightly different way. And it doesn't change dramatically the schedule either. In fact, it doesn't improve it at all, but it just does all the shift, all the movement between registers immediately, and then does everything else. But the total sum, the total length of the schedule has not changed at all. Yet, I think we evoked it when we say loop fission. Why do we do loop fission? Is that maybe it helps us treat in a different way the two loops. And in particular, there is an opportunity to unroll the first one. First of all, because it has no loop carry dependency, and second, because it has no computation. It's just transferring values, right? So it seems reasonable to try to unroll it and see it like this. Now, what has changed here? From the perspective of what I expect in terms of schedule is actually better. Finally, we get something better here. Why is it better? It is better because I can do these 4 assignments in parallel, right? There is no loop carry dependency, so of course there is no, if there is no dependency, there is parallelism, I can do the parallelism. In terms of hardware, is essentially the same hardware. You have to go back and look at the detail. Here there were independent control signals because I was going to do enable this so that I copy this here, then later, in one cycle later, enable this so that I copy this here, enable this so that I copy this here, enable this so that I copy X here. And now I do all of them at once, right? So it's a single control. So the hardware is not changed almost at all, but at least the schedule is a bit better. Of course, the second one is the second loop is the same thing may apply to this one, except that now we know that this one we know has a loop carry dependency, so things are not going to be so easy. If I do unroll completely, something I do obtain though, right? Because the multiplications are not dependent. So the multiplication can be done in parallel. What I cannot do in parallel are the additions, because it's the loop carry dependency, the accumulation. The only thing that I can do is, again, the same trick that we played before in part 1, where we have restructured our sequence of additions. There are 3 additions here to be done, and we can create a binary tree, which doesn't seem to be too different, of course, because it's a small number, but here it is the binary tree of additions, where we do at least 2 of the additions in parallel. So from 3 additions, from 3 cycles for the 3 additions, now it goes down to 2 cycles for the 3 additions. You see, by the way, that it's always the same games, right? That this is a reduction, and the reduction can be done thanks to associativity with some parallelism, and is exactly the same trick that we played before with the hardware. And again, I can do it in hardware because I can put the number of adders that I need. Here I need 3 adders. Before I needed only 1 adder. So you cannot do too many of these things in software, or it depends on the context, but in hardware you can put the resources that you want. This is a good result in terms of timing, because now you get the result much faster than you had here, and with a reasonable level of parallelism, but is maybe not what you want because it's extremely expensive, right? You are having 4 multipliers and 3 adders. You do achieve the parallelism at a relatively high cost. One little comment that I have is that I see here that there are suddenly 2 cycles for the registers, and here 1. I believe this is correct, and is actually just because these are really figures taken from Vivado HLS, and I don't have necessarily a good explanation of why this happens. But once more, this is pretty efficient in terms of timing, but potentially not the best that I would like to have from a perspective of hardware, because it's relatively expensive. Imagine if I have a 256 taps filter, I need 256 multiplier to achieve this kind of performance. So what can we do? What we would like to have is something pipeline, right? There is no pipeline here. This is doing trivial parallelism as much as possible, and then as good parallelism as I can in the reduction tree at the end. So can we schedule things in a completely different way so that we do pipelining? And the problem is that the code that we have has no notion of pipelining. And so I think you start thinking of VLIWs again and what we discussed there, and the software pipelining and so on, because that's exactly what you can achieve from this kind of HLS tools, is to restructure the computation by putting a pragma. Once more, you cannot do it automatically. You need to help the tool to do it, and then you get this schedule that is only slightly worse than this one in terms of latency, but actually as an initiation interval, you can start a new computation every 4, which is particularly good, or as good as you expect it to be. Now, how do you get here? What is hidden in this Pragma HLS pipeline that you have to put to Vivado HLS to do this job and finally achieve the circuit that every good designer would have designed in VHDL or Verilog? Well, what you need to do is exactly the same that you have done for a VLIW. That is, restructure the loop that you have here, which had an initiation interval of 5. That is, you can start a new loop, or the length of the body once, in terms of VLIW, means 5 instructions in the body before you can start a new one. So initiation interval 5. And only 2 operations in this body, that are the multiplication and the add, with the dependency between them. You have to restructure it into having another loop that has a different body, where the 2 addition and multiplication corresponds to different elements or different iterations of the original loop, and therefore they are independent, and therefore they can be done in parallel. And this corresponds to essentially doing the perfect pipeline. If you want this, if you are not immediately clear about this slide, stare at it a bit longer, because this is a way to revisit and remember what we have seen for VLIWs, and is exactly the same thing that we were doing there for software scheduling purpose. Now we are doing here for creating hardware. But that means that this striking resemblance between what we are doing here to create this static schedule that is enforced by the controller. The controller gives all these enables to all the parts of my machine. This resemblance means that what I get also from HLS has the same kind of limitations, the same problems. They don't cope well with variability, with cache misses, if there are caches in these circuits. They don't cope well with memory dependencies. Remember memory dependencies? I hope this is a good way for you to revise, right? Go back and think of VLIWs, think of Itanium. If I have memory dependencies, I have this advanced or speculated load. I never know which one is the two, but one of these special loads that tries to advance the load assuming no dependency and then correcting later, right? Why? Because VLIWs cannot cope with this dependency well. And so this is not going to work well, and we'll see actually better ways in a minute. Both VLIWs and HLS impose burdens onto the users. You have to decide what to do, where to do, and very often make it manually. You change the code to get the result. And this is not what we would like from HLS, right? So we'll try to visit a new way of doing HLS that maybe has some advantages to that, and removes some of these limitations. I have a couple of slides that I'm not going through, but you can go and look at them, at the fact that when I say C++, it seems I mean anything from the C++ programming manual, but of course it's not true, right? You can put in these programs only a relatively small and well-defined subset of C++, probably for, at least in some cases, for clear reasons, right? You cannot do a malloc because there is no memory to invent. You don't have memory. You have only static allocation because you'll put this in the circuit. And then if you want to malloc 1 gigabyte of RAM, well, it's not there. So you cannot do these kind of things, right? Some others are more limitations, more sort of occasional limitations. The other part that I wanted to stop for a second and discuss, because it is related also to why HLS today is important, and maybe being it's still more or less the same tools was not important or not interesting in the 90s. And the reason is that because FPGAs are becoming interesting. FPGAs, I know, I suppose you know what they are, right? Otherwise you look on Wikipedia, but field programmable gate arrays, these circuits that are built but don't have yet a logic function, a hardware function until you load a functionality, they make a perfect host for what you do with high-level synthesis, right? You take your C program, now you convert it into a circuit. If it were possible to have immediately a fantastically efficient circuit, it would be great, because now you put it on the FPGA and you use the FPGA to compute, potentially in a much more efficient way than your processor will do. And now if you go on Amazon and you take an instance with processor, with classic superscalar out of order high energy processors, and an instance with an FPGA, maybe in an ideal world, you will be able to take your C program, compile it for the x86, compile it or synthesize it for the FPGA, and profit from the advantages that the FPGA and hardware could give you. Except that it is a dream, because if you want to do this, you can, but you have to work extremely hard to create a good design for the FPGA. So maybe it works, but it works at an extremely high design cost, and not as simple as saying, oh, I use GCC on x86, or I use Vivado HLS in the FPGA. And so the last part of this course goes and looks a little bit in other techniques of doing high-level synthesis that may have some of the advantages that classic HLS misses to achieve the performance of a given piece of code on an FPGA or on a piece of hardware automatically, without too much work from the side of the programmer. Let's start this part on the different way of doing HLS by an example that will help us understand what is wrong in concrete with more traditional classic HLS. And the example, a bit as anticipated before, is connected with these memory dependencies or control flow. We'll see later an example of control flow issues. But here is a case of classic dependency that is hard or impossible, actually, to detect at compile time. You see the program. I guess you can easily imagine what it is, even from the name of the variables. You're computing an histogram of a monodimensional set of values that are in the vector x. And since you are updating bins with some weight, this update of the bins of hist may be completely independent between two iterations if the x of I and the x of I minus 1 are different, or if they happen to be the same, you're actually updating the same bin in two different iterations. And here is the case, right? Between the first two iterations, there is absolutely no dependency, but between the second and the third, there is a dependency. And is a read after write, so I need to wait for the store to be done before I can do correctly the load. This is exactly, I mentioned it before, but I repeat it, is exactly the same reason why in the VLIW in Itanium, there is this, I never know, a load advanced or a load speculative, because you need to do something. If you don't have any possibility, any special structure like you have in Itanium, and you have to statically schedule this, in other words, if you give this piece of code with whatever optimization you want to Vivado HLS or any of the other classic HLS tools, the kind of schedule that you can obtain is only this one. You have to assume that the load is dependent on the store, because it can be, right? So conservatively, you have to assume a dependency, and you'll schedule it after the load. And there goes all your potential of parallelism, because there is no pipelining possible of any sort, because you need to wait. Now, what you want in reality is something like this. You want to figure out that this load has no dependence from the store, which you can know at this point in time, right? Because you just loaded x of 1, you knew x of 0, so if they are different, there is no dependency, so you can safely go and do your load. And you want, when you see that x of 2 and x of 1 are the same, you will wait. So you lose performance and potential parallelism only when the potential parallelism cannot happen, but in all other cases, everything is fine. So I already alluded to this, and I think you are starting to see where I'm going, right? We know very well where this comes from. Is exactly the same that we have done with the VLIW processors that had all these sort of problems. Now, we know that in some cases, these problems are not important. When you have some well-behaved applications where you can squeeze in, rearrange things, maybe it's not the case in this specific example, but you can do something with a lot of manual optimization to make things work, everybody's happy. If you want to take code and put it on a processor like we typically do, right? We just compile our code and run it. Well, VLIWs don't work so well, and this was basically the story of Itanium that we have been looking at a few weeks ago. And we know what is that we need to make things work, because we do this every day. We use the correct solution every day, which is the one that is in our laptops and in every cloud on computational cloud, which is out of order superscalar processor. That is places where hardware decides when to schedule what, right? At runtime, when some of the problems that may happen are seen, are actually available. And this is the problem that we have in high-level synthesis, is that until recently, and all commercial tools essentially behave like VLIWs, which works very well if you're doing DSP applications, but doesn't work very well for my absolutely generic and arbitrary code. So what we want to do is to try to do something to improve this. So we want to create circuits exactly like we were creating circuits before, but maybe a different type of circuits that will not have these kind of limitations. And the idea is to get rid of this static controller. This is what we have been doing just before, right? We were creating a data path, putting registers around it and so on, and having this controller that was telling each of the components when to activate, when was their moment of glory to do the operation. And what we want to have is a circuit where there is not such a controller, but where decisions are taken locally depending on availability of data. So like here, there will be a communication that is done that is based on handshaking, on the availability of data that will trigger the advancement of computation. Now, I don't know if you have any experience or knowledge of that, but there is a class of circuit that people have been dreaming of since digital design has existed. And people really dream of, because they are incredibly powerful in theory and actually incredibly difficult to implement. Practically no circuit exists in practice that really does this. And this is the category of asynchronous circuits. Circuits where you remove the idea of this clock that is distributed to all the components, but you simply have when something is ready, is memorized in the next register, and everything is done by checking readiness and advancing on readiness. So what we want to do is something similar, but not with all the problems of not having anymore a clock, which again is a disaster in practice, but a synchronous version of it, where we wait for things to happen, but on the resolution of cycles. So it's still a perfectly synchronous circuit, exactly like the circuit that we have seen before, created by Vivado and so on, in cycles. The only thing is that we don't know how many cycles, on which cycle things will happen. This will be determined by communication between the components. So the components have some protocol, and it's not very important what the protocol is, but typically we'll have some handshaking like this valid and ready signal, where component one says, look, I have something for you, and component two says, look, I'm happy to get it because I'm done with what I had to do before. And if valid and ready are set, some data are passed between component one and two. And we abstract this with the notion of token, right? We say that if the correct handshaking happens, there is a token of data that is passed from one component to the next. And then with this abstraction, or with this protocol for communication, we can have all the necessary components that are not necessarily terribly different from standard usual components, right? We can have functional units. They're only a little bit different in the sense all the functionality is the same. The only difference is that they wait for the operands to be true. We don't do an addition on every cycle with whatever comes, but we'll do the addition only if I have two valid inputs available. We have a memory interface that is essentially the usual memory with load and store ports. By the way, if you know a bit memory systems, they typically have some handshaking interface. So it's probably the memory interface is the most standard version, right? You give the the address and you say, hey, I have an address for you to do a load, and you get the data, and somehow the memory system says, oh, look, here is your data, because who knows when the memory system is going to answer, which again is relatively normal for a memory system. We'll have buffers that essentially imagine as registers, but we'll come back with the specificities, but essentially call them registers. We have FIFOs that I think is totally clear what they are. And then you have a number of strange components that we'll see the utility in a moment. For instance, fork, which is a component that takes a token and splits or maybe replicates the token to a number of users. It means that basically it has this handshaking with the predecessor and then repeats this handshaking with multiple users. Join is the dual, is the synchronizer that is dual to this, which waits for all tokens to arrive at its input and then lets them pass. It's essentially the same component that you imagine at the beginning of the adder that I described before, where the addition is done by joining, by waiting for both of the operands before we start. Branch represents clearly decisions, which is what the name suggests to us, right? If we have something that arrives and a decision, we decide whether to send to the right or to the left, or to a specific successor the token that arrives. And merge is maybe you call it phi if you speak compiler lingo, but is essentially the dual component that takes something coming from one predecessor. I don't know exactly which one will come, but from whichever the predecessor I get it, I'll send it on. And again, all these components are just there because they need to sort of handle all these individual handshaking with predecessor and successors, and they are usually very simple. You see a join, right? It's an extremely simple circuit, and is actually extremely easy to understand, right? There is nothing that happens on the data side, but what happens is that you need both inputs to be valid for the output to be valid, which is what we said, and some similarly silly and simple relations, logic relations concerning the rules of Stalin. Some are a little bit more complicated, but it's very simple functionality and very simple logic. So how do we get to synthesize circuits, right? This is, we want to do HLS, so I have a piece of code and I want to get the circuit out of it. And actually it's sort of trivial in some sense, right? Much more trivial maybe to do this, at least apparently, than to do the synthesis that we have seen in sort of chapter 2 of this lecture. Why? Because essentially what we have is a control flow graph, a control data flow graph from the compiler, basic blocks, control flow edges, and in the basic block a data flow graph. And what we can do is essentially rewrite literally this data flow graph, this basic block, in terms of the components we have seen before, right? I have here an I that I need to use to read load of x of I, so I have a load port on the memory. I need to use I to read way, so the same I is used to do a load on way. The I is also used to increment because I need to do this I++, and so on and so forth, right? Each operator is a functional unit. There is an immediate duality between the intermediate representation of the compiler and the circuit that I produce. On top of that, I start putting a bit of the control flow graph. For instance, the fact that I have variables at entering the basic block may came from either of the predecessors of this basic block. And so I put a merge that has this notion of taking the token from whoever it comes. And at the other end of the basic block, I need to decide which successor should get my token. And naturally there is a branch node, right, which has the same name of the instruction that we will put at the end of a basic block. So when I get I plus 1, I check if I is smaller than n, and if it is, I send it on this side, otherwise I send it on this side. And if I send it on this side, this is the second input of my merge that I used before. So essentially, also here, I copy almost literally what is my control flow graph. And then I have a few cosmetic things, right? I need to put a fork on any signal that has multiple fan out, because fan out, if you think for a second, doesn't mean anything when you have, you don't know how to handle fan out when you have this handshaking. So the fork is exactly the component that replicate tokens when you need to have more consumers of a token. And then you have a circuit, right? Now, there is one problem maybe, is that so far we haven't put any buffer, any sort of register, anything, right? This is potentially everything of, here is combinational or without any storage. So maybe there is a sense that we need to store somewhere essentially the variables of our code. Now let's understand this a bit more, and to understand this a bit more clearly, let's understand some of the properties of the buffers that we have. And there are a couple of things that are important to understand. The first thing is that buffers don't behave exactly like registers in our classic synchronous design. So imagine that you have the circuit that you see here, and you now imagine that you want to put a buffer here. Now, I hope it is absolutely clear to you that this modifies the functionality of my circuit in the world of standard synchronous design. Right? If I put a register here, I delay this value, and now I have what I end up summing up, the operands that I'm ending up summing up are not the same as before, because one of the two streams of operands is delayed by one cycle, so everything is wrong, let's say. This is not the case here, though, because if I'm in this kind of data flow circuits, what happens is that when one token does not arrive to the plus because it's stopped into this register, the adder has this internal synchronizer and pushes back the other token and keeps it waiting until both are ready. So there is this notion that adding buffers in this kind of circuits may modify, and definitely modifies, and maybe modifies in a negative sense, the performance, but has no effect on circuit functionality. So unless I care for performance, and at some point I will care, but unless I care for performance, I can put buffers wherever I want, it doesn't matter. The second thing to understand is that if I do circuits as naively as I do, like in the last circuit that I've done, I may have some loops. And now if I take into account the fact that the merge is a combinational component and the branch is a combinational component, and any of these functional units are potentially combinational components too, I have a combinational loop here, which is one of the forbidden things of digital design. So the point is that I need to take any loop that I see, and I need to put a buffer to guarantee correct functionality. There is a second way that is completely equivalent way to read the same rule or the same need, which is to analyze what happens on this loop in the absence of the buffer, and what happens is a deadlock, is a circuit that can never advance anymore. It's, again, an equivalent description of the problem that says the same thing. You need to put one place more for things to be stored on this loop to advance, and this is a buffer, and so you want a buffer. So let's go back to our circuit that we have not yet studied very much, but we have achieved, and we thought it was a good idea. Now we have this problem that we have two combinational loops. Actually, they are mostly the same, but one passes here and one passes here on the left, and they are for the rest the same path. These two combinational loops should not be there. So I need to break them. And one possibility that makes a lot of sense is to break them there, right? Why do I break them there? Because I break them in one of the common parts. So a single buffer is enough to break both. And now I'm happy, right? So let's see how our circuit works, right? At the beginning, we insert a token which says start and says I is equal to 0. It stops in the buffer. It goes out of the buffer on the next cycle, and we expect it to go down the 3 paths and start, in particular, from the path that computes the new iterator to go down there. And we want to go down there and back as quickly as possible, because this will trigger the beginning of the next computation for the next iteration. So let's see what happens. It goes down, and it does exactly what we expect, right? All this is combinational, so you've seen that the token has gone through and finally came back to the buffer. So great. The problem is that now there is something that is not so great, because we would like to have this token to advance, go down, so that it can do this tour again. In fact, what we want to do is that this tour is done on every cycle, so that every cycle we start a new iteration. So perfect pipelining, right? Except that what is happening is that there is this guy down here that is saying, I want two operands to do the addition. And I don't have this operand. So it says to this one, okay, keep your token because I don't know what to do about this. And this guy says, okay, fork, don't give me something because I'm still not rid of the previous token. I'm still busy with the previous load. And what is the result? The result is that this token cannot advance. And actually, this happens on different paths. There is also this path where there is this store that says, oh, I don't have this result, so I don't want what is coming out potentially from this fork, and therefore, this guy will not want what comes from this fork. So the circuit doesn't advance, and what is the concrete result is that the token does not trigger a new iteration, and this is what we get in terms of timing diagram. Initially, we seen the first time everything went well, but after the first time, it doesn't start a new iteration at all until everything is finished in the previous one. And so this is very bad, right? Because the whole purpose of this was to have a nice pipeline, and now the pipeline doesn't work at all. And it's not working because of memory issues, dependencies, and so on. It's just not working. So why is it not working? The problem here is that we need to absorb, we have this back pressure, and we need to absorb on the slow path, right? This is a fast path, and this is a slow path in some intuitive sense. We need to put here some FIFOs that absorb these tokens while we wait for things to advance. So you need to have, and one can prove that there are exact methods to compute the size of these FIFOs so that you absorb exactly the number of token that you need. So you size the token to the extent that it is needed. And if you do that, remember the situation before, you are making back pressure here because you say, I don't know where to send this. Well, now things go well because when this guy wants to go down, he knows that he can put it in the FIFO. The FIFO accumulates and keeps things there until they advance. So, modulo this need to add FIFOs and buffers in strategically important places that I didn't tell you how exactly to do, but there are algorithms to do this, you can have perfect performance. You can have a perfect pipelining. Now, I hope you look at this and you are a bit surprised, right? You're a bit surprised because now I'm super happy because I'm going extremely fast, but in fact, I'm going too fast because nothing is checking in my circuit whether there is this dependence, right? So now I have a circuit that can pipeline superbly well without doing anything. The beauty is maybe you can appreciate that if I implement all these things in my tool, I don't have to do modulo scheduling or particular forms of rearranging the code. It will do this, but unfortunately, this is wrong, right? So we need to figure out what to do with memory and how to handle this kind of dependencies. Now, how do we handle this kind of dependencies in superscalar processors, right? Again, it's a problem that we have everywhere. Who determines whether I can or I cannot, let's go back maybe to the example here, who determines whether I can or I cannot execute this load, knowing that there are these two stores that are still pending, they are not done yet? Who does this? I hope you remember. And again, this may be part of the course, is a great place to revise what we learned in the first classical computer architecture part of the course, because again, the question is, who did it there? Who guaranteed that things go well? And if you remember my arrangement of the reorder buffer, it is through the reorder buffer that you do this clearly, right? You go down, there were a couple of slides, you go down and you look if in the reorder buffer there are pending stores, and you look if they have the same address that you have. In this case, all of them have a known address by now because you loaded all the addresses, so you know all the addresses. And if they don't collide, you execute the load in front of the stores. If they do collide, you keep the load pending until or actually you even bypass and you get the value from the appropriate store if you have it, or you keep it waiting. So this was the way we did it. And actually, I remember, I think that in the slides, there is this comment that actually in practice, people do it in a different structure that is essentially equivalent to the reorder buffer that I showed in the slides, but is actually a load store queue that is specialized for this job. Again, the job is the same, the place where it is done is different. Now, there is one part that is important in this load store queue. The problem is that the load store queue needs to know what was the original order, right? Like the reorder buffer decides how to potentially reorganize and execute things out of order, go and fetch, go and do the load before the store is done. But this only by knowing what was the original, the correct by construction, by definition order, right? Which is the order in the program. And one of the things that one realizes as soon as you say, okay, so what we need in our circuit, in our data flow circuit here that we have just designed is a load store queue. Because it's the same problem, it's exactly the same problem. So if the load store queue solves it for the processor, well, it will solve it also for us. There is one problem though, right? When I look at a data flow circuit, I have no idea anymore of the order. Maybe this example is not particularly beautiful in the sense that here I can imagine, I can detect that the order was this, 1, 2, 3, because there are data dependencies between these, and these data dependencies in this particular example still suggest what the order is. But you also understand that there could be in a completely different part of this basic block, completely disjoint in terms of graph, a write, and I have no idea if this write was written by the programmer before or after this reads. And what matters is where they were written by the programmer, right? But this is completely gone in this representation. So the problem is, I cannot just get them and do something when I get them. I need to know where they were in the program. And the idea that one can have is to say, well, within a basic block, I know the order, right? Because it's how they are written, right? Is there in front of me, statically determinable, is absolutely clear. What I do not know is how the order is between different basic blocks, because I don't know after one basic block what is the next basic block. It depends on control flow, right? So if I execute this, I don't know if after this store there will be another load X, because I execute the same basic block again, or if after this store there will be some other access because I go and execute some other basic block here. So the idea is this, is I can put into the load store queue for each basic block that can occur the list of the loads and stores in the order they are from that basic block. And every time that I'm starting a basic block, I tell which basic block I'm starting to the load store queue, and the load store queue insert this list at the end of the queue. Says, oh, the next accesses that are going to be made are these loads and stores. So essentially what happens, this replaces what in my processor is the fetch and decode, right? I start a basic block, I go through it. The first thing that happens is that I fetch and decode these instructions and I allocate them. Here the allocation is done with this, and every time that I go through a basic block, I allocate in the queue. Apart from this, the queue now works exactly like the queue that I have, that will let loads execute before stores only if they don't collide, and which includes the fact that I know exactly their addresses, and so I can safely execute them before the store. Now, if you do this, and of course you have to implement, but it's not terrible to implement, right? I think you understand that once you change something in the allocation, because it doesn't depend on a fetch and decode unit that doesn't exist here, but once you change a little bit in the allocation, all the structure of the load store queue is exactly the same that we discussed in the course. We discussed it related to the reorder buffer, but is exactly the same, right? It's the same behavior. So if I have a circuit for a load store queue, I can use it also here with minor modifications. And once I do this, I obtain exactly what I wanted. That is that my load, in case where it has to be postponed, is not executed here, but is held until it can be done correctly. And whenever there is independence, when I'm here and I know exactly that X1 and X0 are independent, I start executing this load because it is completely independent and there is no problem. And I exactly achieve what I want. So if you try to do this for real and you look at how you do compared to C11, the static result, this is Vivado HLS in this example, and I do my versions, so everything is normalized to the results of Vivado HLS. I do slightly worse, in fact. So again, Pareto domination, right? This is execution time. The smallest is better. This is resources. The smallest is better. So in case there are no problems of disambiguation and so on, and a perfect pipeline can be designed statically. Remember the example of FIR is what we did before, and although we had some troubles to get the circuit to really work, but in the end we had a circuit that was perfect. In those cases, if we do the FIR with this technique that I just discussed, we end up not being so good in terms of timing and putting in maybe twice as many resources, which is bad. right? Again, we are Pareto dominated by the static solution, which is better. Yet, as soon as there are conditions in the loops or memory accesses that cannot be disambiguated, we do way better, right? In terms of execution time, we are a factor faster, like 3, 4, 5 times faster, at the price of resources. But again, all these points are Pareto optimal compared to this. If you want to be fast, you need to pay. If you pay, you can get much more performance. And the point is also that you can start going in directions that were in some sense prohibitive, impossible in the world of static scheduling. What are these things? Are exactly the same things that we do regularly in our superscalar processors, like speculation. So here is an example of where you want speculation. It's a case where you have a condition that arrives very late, right? You have to do a computation. This computation takes long because it's a float, and you take a decision only after having done the computation. And so you don't have any chance of parallelizing this loop. It's not very dissimilar from one of the examples, from the example where I was showing you the first schedule that we built manually for the VLIW, where we had essentially zero parallelism because we had to finish everything, right? In this case, it's very fundamental. The reason why we have to finish everything is that we need to wait. And like in that case, if you remember, I asked you the question, but would we do better on that with a superscalar out-of-order processor? And the answer was yes, because we start the next iteration before. We don't know yet if this iteration has to be done, but if I start before and I don't do damage, in the sense that I don't corrupt memory by doing something that I should not be doing, I can continue until the moment that I figure out that I need to stop, and then I just kill what I started doing because it was crap. So can I do this in this situation? Here is a view of why things don't work well, so that we can better understand what the solution can be, right? Again, I have my circuit that is the literal translation of this, like we have seen before. I have my token that enters, that should go down the 3 paths, and it arrives at the branch my token. But this token, to advance here and trigger the next iteration, needs also to know the condition. And unfortunately, the condition comes from this low path, because this is the situation in the code, and then it will take time, right? It will need several cycles to do the loads, to do the to pass through the different stages of the floating point adder, and to do the comparison, and only then finally the token can go back. Right. So the situation is exactly the same as the one of the statically scheduled high-level synthesis. So we're not doing any better, but what we can do is that we can introduce the notion of speculation. I'll not go into all the details, right? But the idea is that we can have components, and it doesn't matter which components, but any components that we want, we can invent a speculative version of it. Imagine it is a branch, and it is a branch that sends the token wherever it thinks it should go, even if it doesn't know yet the outcome, it doesn't know the conditions yet. And it sends out the token that is of a new type, that has a new bit in the story that says, look, I am speculative, I'm not a normal token. And then what is the problem? The problem is that I start producing results that are potentially wrong. And remember our discussions in superscalars, what is the danger there? Is that I start modifying the state of the machine, which essentially means registers there, but we don't have registers here. We start modifying memory or other things observable by the user before knowing that they are correct. So what we do here is that we insert some commit units that essentially block anything that arrives that is speculative and wait for some confirmation that the speculation was correct before releasing. And where are these commit units? Well, they are before storing something in memory, which is doing damage, or before communicating results to the user, because it's again doing damage. I tell you a result and then I come back later and I say, oh, by the way, it was a mistake, right? So I stop these tokens there. And the last thing that can happen and that I need to take care is that the speculator may send a wrong token, and then I consume a token from here to do a calculation, but then it turns out that it was wrong, and then the speculator will say, send the right token, the correct token, but now I consumed this value. So I need to have some units that save this value so that I can use it again if I need. And again, you can, I think it's a great exercise to try to think and make a comparison between what happens in this circuit and what happened before in our superscalar processor, because you will realize that everything that you do here, in some way, you did there, right? Part of the register renaming is that you are keeping available the operands that were involved in the non-committed operations, in operations like this that is not committed, you were keeping it renamed and available until you were sure that you will not need this anymore. And this is exactly what you do here. And all this is controlled by the speculator that takes this initiative of sending tokens that may be wrong. And therefore it tells, when it sends one, it tells to all the save units, look, keep your token because maybe we need it again. And it needs to tell when it's finished to the commit units, throw away the token because I made a mistake, or keep the token, send the token forward because it was a good speculation. So you have these areas of code, of circuit, but I see my mistake speaking, corresponding to areas of code that are speculated in our processor. And you have these units I already explained. I think they are super clear, right? For instance, there is this speculative branch that received the token from here and decides to send it on the right, but had not received the condition. And so this token is speculative. When it receives the condition, it will figure out what is correct, whether it was correct or not. And it will need to resend the same token, right? So what it will need to do is to save the token so that once it will figure out that it was sent in the wrong side, it will take the token that was there, and then it will send it from on the right, on the correct side. So these components are relatively simple, not super simple, but you see they are made of the usual components, right? It's still forks, buffers, branch, merges, and the branch that throw away something or makes it advance. So it's actually relatively elegant the way you can do. You have this commit unit. I think I said it already. It doesn't need really much, but essentially it lets it pass if it was correct, or it drops it. And again, they are simple components based on essentially the same set of building blocks that we have. You need to place this save and this commit units. The intuition, I think, is very simple. You want to have the save as close to as possible to the place where there is this interaction between the non-speculative and the speculative components, so that you save the least amount of information possible, or actually you replay it as close as possible to the consume. And at the same time, from the commit perspective, you want them as far as possible from the speculator, in the sense that you do as much computation you can with the speculative token until it becomes really dangerous. So you really push it until the store, for instance. The components are not terribly different from the speculative components are not going to be very different, in the sense that the support for this speculative bit is just an additional bit that is in most cases just propagated, right? The buffer has one bit more to remember that this value received was speculative, and when it will be transmitted to the successor, it will be still speculative. And in some cases, there will be something that will say if any of these two operands that I received to compute the addition was speculative, then of course the result is also speculative. What happens to our circuit? Well, if I put the speculative branch and I put the save unit, the commit unit before the end, and a few other units that need to be there to avoid an interaction, in principle, everything should go well, but if you look at it carefully, it has some problems. I think this is beyond the kind of information that I want to give you in this lecture, but you can try to do this example yourself and see what happens. The problem is that it starts sort of well, in the sense that there is this speculative token, that is the red token that we just have seen, that comes down, but unfortunately it stops in this commit unit, because you cannot speculate twice in some sense on the same token. It's already a speculative token, it cannot go back directly to the speculative branch, and so things block now. So go advance one cycle more, but then block and advance only a little later. So it's again a bit like we have seen in another situation, where the first time everything goes well, but then things doesn't advance. And the problem is that you can speculate once, but somehow you cannot speculate twice. So again, these are details that are not extremely important, so pay only the attention that you care to this. But essentially you can do, when you have this succession of a commit unit and save unit on a cyclic path, on a loop essentially, you can do a version of this save commit unit that does the function both of the save and commit, but actually lets a speculative token pass, so that you continue to speculate on this first on this speculation, and they expect a number of then confirmation or a rejection of the quality of the speculation. So they contain a few more things, and when you use them, since they let the token, the speculative token, go through to come back, everything works well, and you get exactly the performance that you want. So again, you can do your examples and your experiments and compare with the usual traditional HLS, which is essentially Vivado HLS, for instance, in these examples, and have a bunch of control-dependent, limited pieces of code that are actually very classic and simple piece of scientific computing, where you do have, in reality, a lot of control domination, because you do test, right? For instance, you have here Newton-Raphson, right? And you probably know what it is, right? Is one of the classic numerical algorithms. But if you do it, Newton-Raphson has the problem that is an algorithm that converges well in most cases, but in some cases it doesn't converge. So you need to make it really work beyond the textbook, you need to check for some condition and see if that condition is true. And depending on that condition, choose a different iteration that is not a Newton-Raphson's iteration to advance and to get out of that problematic situation. And this is bad for for practical situations, because you need to wait for this test and figure out if this test is true or not before you start doing the computation. So it's one of those cases that are real practical cases of code that you really need to execute, where it makes a lot of sense of doing speculation, and speculation pays off brilliantly, right? You see here is maybe even almost 10 times faster for only, because it's only 80% more area, right? And so these are things that you can do only if you change completely your paradigm, moving away from static scheduling, and you do a dynamic schedule which changes depending not only on scheduling opportunities, not only on dependencies, but changes also on what is the outcome of branches and whether your speculation was wrong. So this concludes the third part. I hope you enjoy somehow how doing hardware from code has exactly the same difficulty, if you want, that you have in creating processors for general purpose code. You have the same choices, you have the same limitations. In some sense, you have the same kind of overhead. We said at the beginning, if you want to do a VLIW, you think it is probably a good idea because you put much less hardware. If you want to do a superscalar out of order, you're going to have to pay for all these buffers, the order buffer, reservation station, associative searches, and so on, that will cost you, right? And qualitatively, the same thing is true here. Partly, the choice between these two things, these two approaches, depends from the same considerations that you have in choosing between a VLIW and superscalar. If you care for out-of-the-box performance, if you have control-dominated algorithms, it's absolutely sure you want a superscalar processor, and maybe here you will want a dynamically scheduled HLS. If you are running things that are perfectly determined at static time, you know exactly your application, you can put the time to optimize the application, you will want to have a VLIW like you have, as I mentioned, in your smartphone for everything that is signal processing, like your voice filtering and so on and so forth. If you are doing HLS, you can do classic HLS for that, and it will be certainly the best result that you can have. You have here a few references on the different parts of this lecture. And the third part is actually work that we are doing right now in my lab. Lana Josipovic is actually the person that is doing this work. If you are curious, you can go on dynamatic.epfl.ch. We have open sourced our HLS tool, and it is available, therefore, for everyone to play with. Thank you very much, and see you next week or in 2 weeks, depending on when you are listening to this.